This is AQA A-level chemistry. We are on the year 12 topic alkenes, and this is part 2. In the first video we looked at nomenclature and isomerism, and here we are going to focus on the electrophilic addition mechanisms that you will need to be familiar with. I will say at the start that this video does not cover major and minor products in asymmetric alkenes. That will be in the next video. Okay, so when we take a look at alkenes, as I've already said, they undergo electrophilic addition reactions. It involves heterolytic fission, which I'm going to talk about a little bit later on. But what do we actually mean when we talk about electrophilic addition? Whenever we're looking at mechanisms, I think it's important to try to understand what's happening rather than try to remember it as a snapshot. So if we take these words and piece them together, we can hopefully find a logical way to understand and remember them. So, electrophilic. If we take the word literally, we mean a lover of electrons or a lover of the negative charge, but we would never write that down in an exam. If it loves the negative charge, that means that it's attracted towards electron-rich areas, and that means that it's an electron pair acceptor. And the word addition is really straightforward. We are simply adding new components to our compound, so something new is going into it. But again, if we think about that logically, if we're adding new things, we need to get rid of some bonds in there. So we are always going to see the breaking of a double bond in an addition reaction. And if we can remember that, if we can see that addition mechanisms involve the removal of a double bond, elimination mechanisms involve the formation of a double bond, and substitution involve replacing one thing with another, you start to recognize them rather than try to remember a name that goes with a mechanism. But let's take a look at the mechanism itself, and let's use XY, which has been given a delta positive and delta negative charge, the X being delta positive. Pause the video and have a go at the mechanism for this reaction. Okay, so I'm going to start by drawing out the display formula of the alkene, which certainly in this circumstance is worth seeing. And I've not written the delta positive and the delta negative onto the XY. We know that X is delta positive, and you'll notice that I've drawn that closest to the double bond. That's for a really important reason. Now, when we then go through the mechanism, what we can think about is where is there going to be an attack? And if I've got a delta positive X and an electron-rich double bond, there's clearly going to be an attraction there. So my first arrow is going to go between the two. But you'll notice I've not put an arrowhead on. Often when people look at this, if they aren't confident, if there are misconceptions, they will think that the electrophile is attacking, and so we're going to put the arrowhead up at the top, but that's not the case. Remember that a curly arrow represents the movement of electrons, always from electron rich to electron deficient. So this is going to go towards the delta positive. Now that essentially means that we are creating a bond between one of the C's and the X, because those electrons are transferring down. X had one bond, we're now forming a new one, so it can't sustain the XY bond. So again, we show the movement of electrons that reflect what's going to happen, and the electrons in the covalent bond move towards the Y. Now from there, we are going to create an intermediate. And as I've said, I've got a CX bond formed, but I've broken the double bond. That means I've only got 3 bonds around this carbon. That's not going to be stable, but that's not the end of it. That actually now has a positive charge. And again, if we think about this Y that has taken electrons from the bond that's been broken, that's no longer delta negative, that's negative, and it has a lone pair. So hopefully what we see here is a very clear attraction between a negative Y and a positive carbon. Remember again, the curly arrow will represent the movement of electrons from electron rich to electron deficient, so it goes very clearly from the lone pair, not the Y, not anywhere else but from the lone pair, and it goes to the carbon that is positively charged, the carbocation. And then finally, we've got a question down here at the bottom. Where in this mechanism has heterolytic fission occurred? Well, heterolytic fission, it's said in one of the boxes earlier in the video, involves the breaking of a covalent bond. It's happening here essentially where the XY bond is broken. Okay, let's take a look at what happens with actual electrophiles that you need to learn about. So HBr in the first instance. Have a go at completing this mechanism and then review. So we have got our ethene drawn out. I've got my HBr. You'll notice I've got my H closest to the double bond. And we need to remember that in electronegativity, the bromine would be delta negative. And once we know the hydrogen is delta positive, we know that our first curly arrow is going to go from the electron rich double bond and it's going to go to the delta positive hydrogen. That means that a CH bond has been created. H can't sustain the bond with Br, so we get the electrons going from that bond to the bromine, and we are well on the way through this mechanism, and we've generated a couple of marks already. Now that takes us to our intermediate. You're going to see similarities in all of these. There's my new CH bond, but my carbon is now a positive carbocation, and my bromine, because it's gained that electron, the electrons from the covalent bond have moved towards it, is now Br minus with a lone pair. My final mark, my final part of this mechanism is the arrow from the lone pair going to the positive carbon. So how about if we take a look at bromine as an electrophile? And this might initially seem unusual. Why would it be unusual that bromine acts as an electrophile? Well, if I draw out bromine and I think about what would happen in terms of electronegativity, there is no difference in electronegativity, so there is no permanent dipole. So why would there be an attraction? Well, let's have a think about this question. How could a dipole be induced in a molecule of bromine gas? To answer this question, I'm going to draw out, as I would in the mechanism, my ethene and my bromine. And I've done it vertically below again because that really lends itself to representing what's happening in the reaction. And then if we look at this, we can remind ourselves that this is a really electron-rich double bond. There's two pairs of electrons there. And the impact that that's going to have is that it's going to repel electrons within the Br2 molecule. It's going to push them away. And that means we're going to get a delta negative bromine because the electrons are pushed away from the double bond. And this is going to be delta positive because that's going to be electron deficient. So with that in mind, what will the mechanism look like? And you'll notice here that needs to change to ethene. So you're going to start off with your ethene and your bromine molecule drawn out. And then we've got the first arrow from the electron-rich double bond to the delta positive bromine, which is the one closest to the double bond. And we then get the next mark for the arrow from the lone pair back to the other bromine, taking us to the intermediate. Now you can see the CBr bond that we've created. We've got the positive carbon now, and we generated this Br minus ion with the second arrow. And we can then see very, very logically that we're going to go from the lone pair, which is very negative, to the positive carbon to take us through the 4 marks for that mechanism. Now you have come across this before. You've learnt about this reaction at GCSE. Where is that? Let's draw out the equation so we can hopefully recognise that we start with C2H4, we add Br2, and we end up with C2H4Br2. You might still not be there yet, so let's have a look now at some observations that we might make in this reaction. Bromine water is brown. Now C2H4 is colourless, and C2H4Br2 is colourless. So when I add Br2 to C2H4, I lose the brown colour of the bromine and I end up with a colourless solution. We can now show mechanistically the test for alkenes. Okay, let's move on to the final electrophile, sulfuric acid. Your first task here is to try to draw out the structure of sulfuric acid, actually showing the display formula or close to the display formula. Now hopefully you recognise that sulfuric acid looks like this. It's an S with 2 double bonds to O's and 2 OHs. We're not going to show it that way within the mechanism. We can simplify it to HOSO3H or HOSO2OH. And the way that I often recommend that you remember this is HOSO or HOSO2. And that's really going to keep in mind an audio memory to help you to remember the structure that you're going to write down. So there they are. Either of those is valid. And let's just take a look how this fits with previous structures. My H's are delta positive and my OSO3H or OSO2OH, depending on how I write it, will be my delta negative. Other than that, the mechanism follows exactly the same pattern. So with that in mind, have a go at this mechanism. And here we've got the ethene molecule as previously, and you can see my HOSO3H written out in a format that fits with the general mechanism we've seen time and time again. My delta rich double bond, I'm going to have an arrow from there to the delta positive hydrogen. Because of that, the HO bond can't exist anymore, so my electrons move to the O. That means I've created a CH bond. I've got a positive on this carbon, it's a carbocation, and I'm left with an OSO3H minus ion. Once I've got that, I can hopefully see my lone pair is going to attack the positive carbon, and that's going to take us to our ethyl hydrogen sulfate. Now this reaction does not stop there. With that in mind, have a go at these questions too. And when you write out the structure of the ethyl hydrogen sulfate we've made, you can see CH3, CH2, the OSO3H coming off the second carbon. Now if I add water, I make two products. We're told that we're making an alcohol. In this case, it's 2 carbons long, so it's ethanol, but we're also going to be left with H2SO4. Now, because I started with H2SO4 and I've ended up with H2SO4, that essentially means that it's not been used up in the reaction. So the sulfuric acid here is acting as a catalyst. And what we're actually seeing here overall, because we're adding water, in this reaction, we're seeing a hydration reaction. Now, just to finish off, I want you to see the link here between the mechanism that we do, where you learn about sulfuric acid as an electrophile, and the work that you've done in the alcohol topic, where we learn about the direct hydration of ethene with steam. In that case, we use concentrated phosphoric acid, but the reaction is identical. Okay, that takes us to the end of this video. Thank you for listening and goodbye.